Hello and welcome to the Daily Space for Monday, June 25th. My name is Dr. Pamela Gay, and today I'm going to take you on a fast-paced journey through, some of the latest journal articles coming out in astronomy and space science. It's a slow news day. This morning I went through and I reviewed all of the press releases, which went really fast because there were zero. Then I went through and I reviewed what was going on in the journals, and today I'd like to bring you a few key papers, well, maybe not key papers, but a few papers that were interesting to me. And I see that some folks are reporting that there's slight audio problems. Let me see if I can improve this any. Let's see, that should work a little bit better. Okay. So for today, June 25th, I am going to give you a roundup of some journal articles. And the first one that I'm going to bring you is one that really starts to talk about how we do science. Now, as you may know, we are constantly trying to figure out what is our place in space. And this is complicated, and I don't mean this philosophically, I mean this quite literally. Where are we? Trying to measure this is a complex problem because we can't just go out with a light years long meter stick and measure our distances. Instead, we have to rely on what we call the cosmic distance ladder. This is where we start out by measuring distances to objects so nearby that just by moving the Earth from one side of the sun to the other, which happens naturally, we can see nearby objects appear to move against background objects. So the way to think about that is, if you hold your thumb up and block out my face right now, and I'm doing this right now by blocking out my left eyeball in the screen. Now, when I look with my right eyeball, it's directly in front of the camera. When I look with my left eyeball, it jumps sideways. This is because my thumb is closer to me than the camera. And I can measure, if I know the distance from my eyeball to my thumb, I can measure the distance to my thumb by seeing what the angle of that distance is. Sorry, I said that entirely wrong. If I know the distance between my two eyeballs and I measure the angle my thumb moves from side to side, that allows me to measure the distance to my thumb. Now, unfortunately, not all the stars and galaxies that we're interested in are close enough that we can get this kind of a parallax measurement. And we end up relying on parallax that we're capable of getting from the Gaia mission. So here we see in this graphic a new parallax limit. This is what we're able to get with Gaia. You also see in the center, and let me see if I can highlight this for you. You can see here in the center the old parallax limit where we were only able to measure the nearest stars. So now we're able to start measuring Cepheid and Arillari variable stars out to greater and greater distances. These are pulsating variable stars that the amount of time it takes them to change in size and also change in brightness is directly related to their average size and their average luminosity. We can thus use them by knowing how much light they actually give off, and by measuring how bright they appear, we can calculate the distance to them the same way our brain naturally calculates the distance to a motorcycle based on how bright we see its headlight as. Now, this allows us to start to get to nearby galaxies. It allows us to start to see supernovae. And then we have to rely on supernovae to get the rest of the way out. Now, the problem with all of these different parts of the story is we have error coming into these measurements at every different step in the relationship. And trying to figure out what all the different errors are is a bit of a challenge. As an observer, we just want to go out and look at all the things. And sometimes we need a little help from a friend. In this case, our friend is the theorists. There's a group of theorists working at the computational science group, in the Institute for Computational Sciences in Zurich, who've been going through and trying to get a handle on what are all of the different errors, what are all the different variances in the different kinds of measurements that we make to try and understand our universe, and to make accurate measurements of how is the universe evolving in shape and size in its earliest days? How is it evolving today? And using these measurements to predict out to the future to see how we're going to be evolving, well, as our universe winds down to an end. This is the kind of journal article that actually requires having a table of context at the front. Now, this is work that starts out by saying it's a whole lot more complicated than what we wish it was. And it points out to all of the observers, these are all the different things that we have to take into account. This isn't the kind of paper that says, here are the answers. This is the kind of paper that says, here's how we figure out if the answers we think we have are actually correct. And the reason I'm bringing you this paper today is not because it has any extraordinary results, not because it is going to have any journal articles written about it, but because it tells us how we need to do our science. Right now, we have this major contradiction in observational astronomy, where when we look at our measurements of the universe's expansion, considering only data from, the earliest days in the universe, when we look at data from the cosmic microwave background, when we look at data that takes into account our earliest measurements of cosmic baryonic oscillations, trying to understand how was it our universe was created, we get one set of measurements. And then when we look at our nearby universe, when we look at how it is that we're able to, measure distances in our nearby universe, currently we get different values and they aren't within error bars of each other. And I will post the link to this paper as soon as my computer will let me. I'm sorry, I am dealing with a whirly rainbow right now, and the whirling rainbow won't let me post the link. I'm so sorry. As soon as I can overcome that whirling rainbow. So anyways, I just wanted to make it clear, science is the kind of thing where it takes all kinds. It takes the observers out there doing the very careful measurements, the very careful data processing. It takes the theorists to help us parse out what are not just the observational errors, but the theoretical errors that also get tied into how we interpret what we see. And it's only by taking all of this into account that we can eventually get at, what are the things we know, what are the things we don't know, and what are the places that we know nothing about? So one more step forward. Now, the next paper that I'd like to bring you today is literally one I picked because it was something I have heard nothing about. Our universe is vast. This is an idea that you probably hear on a regular basis. There are more things out there. There are more things in heaven and earth than can ever be understood by man. But we're trying to understand all of them. All of humankind is working to understand all of these different things. And in this particular case, what I did not know was even a thing is something called zebra patterns in solar radio emission. It turns out, and this part I did know, our sun is not the most constant of stars. It is constantly varying, pulsating, oscillating at very, not dramatic frequencies and amplitudes. For a variety of different teams, though, these oscillations show up in a variety of different wavelengths. We have been working to understand solar oscillations since the early 90s, when we began to place observatories around the world that would allow us near 24-hour observations of the sun, that would allow us to get at these low frequency oscillations in the surface of the sun. Nowadays, we have amazing spacecraft such as Solar Dynamic Orbiter that have taken up this job for us and are providing us with terabytes of data a day. But all the excitement is not restricted to optical wavelengths that you could see with your eyeballs. It turns out the kinds of color of light that we more frequently associate with AM, FM bands and, well, talking to our friends on a ham radio, it's actually those bands where the sun starts to get more interesting. Now, in this graphic, you can see a variety of what actually do kind of look like tiger stripes. And in what may be one of the hardest to read graphics I have ever encountered in a journal article, they list the frequency up the side and they list time across the bottom. These are two different polarization bands. This means that we're looking for light waves that are rotating in different directions or oscillating in different directions. To better understand this, it's much easier to take your sunglasses, put them on your face, look at your phone screen or your camera screen, then rotate your screen 90 degrees and you may find your screen disappears. This is because the polarization will block out light that is aligned in one specific direction. Now, in this particular paper, they're trying to understand how it is that our sun has these amazing outbursts that appear in different wavelengths at slightly different amplitudes and at different times. So as you look across this, you can see this is changing with time at different frequencies. So when the sun has an outburst, it has oscillations of bright bands of radio light and dark bands of radio light. It's thought in this particular paper, which I've linked to in the chat, which is by G.P. Shrenknov, Vivi Formichev, and R.A. Sink, that and they're working at the Pukova Institute of Terrestrial Magnetism, Ionosphere, and Radio Wave Propagation in Russia. They're thinking that this is caused in part by Doppler shifting effects, as well as by interactions within the plasma. So imagine, if you will, that you have plasma moving in different directions. It's getting accelerated, it's interacting with one another, and one of these radio bursts goes off. We're going to end up detecting similar light in a variety of different velocities, which appear as different frequencies when we look at it. And this is what leads to this amazingly complex structure. Now, there's a certain amount of scattering going on, and it's just kind of cool. And so I learned something new today, so I decided to inflict it upon you as well. This is one of those rare times that astronomers have named something in a way that actually matches what you see. So welcome to my new knowledge of the day, which is that the sun has zebra patterns in its radio emission. And in our final story, we move much further out in the universe. In this case, we are looking at active galactic nuclei in distant galaxies. Now, active galactic nuclei is a term that's used to encompass a whole variety of different objects. Quasar are one kind of active galactic nuclei. Some of you may have heard in the past of Seyfert 1 and Seyfert 2 type galaxies. All of these different words are referring to galaxies that have a black hole in the center that has material actively streaming in towards the black hole, and as it streams, due to conservation of angular momentum, the material can't go straight into the black hole, but instead it ends up spiraling and shedding its velocity until it finally falls within if it's lucky, within the event horizon. Now, as this material spirals in, it gets heated up through interactions with other material. This is a region of not just like one atom falling in at once, but rather we have vast amounts of gas and dust steadily streaming in towards that central supermassive black hole. And as it does so, you end up with amazing pressure built up in this system. And with extraordinary pressure, with extraordinary densities, the accretion disk will actually start ionizing particles. This drives amazing magnetic fields, and some of the charged particles, instead of falling into the active galactic nuclei, instead of falling into the black hole, will instead get shot through these magnetic fields to go streaming far away from the system. Now, what we see here is in the blue, this is extraordinarily hot gas that has been heated so much that it's giving off light in the X-ray. What we see here is radio emission that is linked to that magnetic jet and particles channeling through that jet and giving off radio wavelengths of light. You can actually see right here in the center of this optical light, that's the full extent of the optical galaxy. So we have a vast sphere of X-ray emission tied to the hot material surrounding this galaxy. We see the radio emission, and down in the core, well, we have a galaxy that is mostly visible as just this accretion disk. Now, one of the things that happens when you have an active galactic nuclei and one of these hot, dense accretion disks is not only do they create this magnetic field that generates the radio jets, but when this material gets hot enough and dense enough, it actually starts undergoing nuclear reactions. In new work by W. Ishibashi, A.C. Fabian, C. Rishi, and A. Salati, working at a variety of different universities all around the world, what they find is that a combination of different factors generated by this hot, dense disk is actually capable of shutting off the AGN from continuing on forever. So what is happening is, as the material flows in, it begins to generate nuclear reactions, just like the inside of a sun. As the hot, dense gas has these nuclear reactions, it generates light. This light generates pressure. When the accretion disk gets sufficiently large and sufficiently bright, it generates so much light pressure that it begins to push back out at the surrounding material that's trying to stream in. And it essentially chokes off the active galactic nuclei. This is called feedback, and it generates a forbidden region within the galaxy. It's this area between the edge of the active galactic nuclei and the rest of the galaxy where material that's trying to flow in quickly gets, well, blown apart by the light from the accretion disk. This particular feedback mechanism, the majority of the models that we've worked on have taken into consideration, well, all of the radio pressure in the system. But one of the things they haven't looked at very much is the effect of what's called radiation trapping. So as the light is trying to escape from the active galactic nuclei, it doesn't go in a straight path. And the same thing is true down in the core of our sun. There is within our sun a region where light, as it escapes, ends up getting absorbed and re-emitted, absorbed and re-emitted, and does this Brownian motion trying to escape, where every time it's re-emitted in a completely random direction. Well, it turns out that in galaxies, you have a similar process, in this case called radiation trapping, where light that is in the process of trying to get out, to push out, can get trapped in this system, getting absorbed and re-emitted. And this changes the size of this forbidden zone. Now, the reason that we're only now starting to take this into consideration, even though it's something that we've known the possibility about for a long time, is this isn't something we can actually observe. So this is the kind of science we do in a computer, where people sit down and they write complex models using the significantly faster and faster computers that we're developing year after year. And through complex software and complex models, we're able to add new factors to our simulated view of the inside of galaxies. And we're able to slowly but surely bring our models into correlation with what we see with our increasingly high resolution telescopes. And right now we're at this special moment where our computers are more or less able to keep up with the detail of our advancing telescopes, and our advancing telescopes are more or less able to keep up with our advancing understanding for models. And this is how we get at the how of what the universe is doing. How comes from computer models, what comes from telescopes. And it takes both working together to figure out what's there and how it works. And again, this is how we do science, one incremental bit at a time. And those are the stories that I have for today. So thank you so much for listening. I'm going to take questions in a moment. For those of you who tuned in late, this is, as it says above my head, The Daily Space, and I am Dr. Pamela Gay. This is a production of CosmoQuest. We're a multi-institutional collaboration here on Twitch as part of our day job, where we are trying to bring you what is new from space and astronomy and put knowledge in your heads. This collaboration is run out of the Astronomical Society of the Pacific and includes collaborators from the Planetary Science Institute and Youngstown State University. If you like what you see, give us a follow so that you'll get every new announcement of when we're going live with science. And we are a nonprofit, so really all of your subscriptions and every bit really helps. So I see that we have questions out there. Phoenix is asking, do we see the same thing with Andromeda, X-ray and radio being far larger than the visible galaxy? So with Andromeda, thank you so much for the cheers, DJ Astro Boy. So with Andromeda, it doesn't have an active galactic nuclei. This means that while we do see hit or miss some X-rays, they're not nearly this exciting or this profuse. In general, the kinds of X-ray objects that we're excited about in Andromeda are just small things that are rather excited. So we get X-rays from things like white dwarfs that are cannibalizing material off of their neighbor. We get X-rays from pulsars and other such high-density objects. We see bits of X-ray in our own galaxy, but it's mostly echoes of when our own supermassive black hole ate one object or another sometime in the past. We don't see this ongoing radiation. So I'm so sorry that I see so many people having computer difficulties. I'm not entirely sure why Twitch sometimes lets us change bitrate and sometimes doesn't. I know I was having problems getting on Twitch earlier today, so it could be that they're pushing new updates. So I see that there's a question from Graham HW. Any news on Betelgeuse? Betelgeuse is the bright red star in the shoulder of Orion that is considered to be one of the stars most likely to go supernovae. So far it hasn't, much to the dismay of everyone who wants to see Orion develop a bloody red nebula of a shoulder that is visible during daylight. And were the supernova to go off right now, while I wouldn't be able to see it due to rain, it would be a daylight object for all of you out there who have clear skies. Azuriel Palin is asking, they recently learned that there's no bow shock between the interstellar medium and our sun's reach of influence. Is there anything else cool to know between us and the interstellar medium? So one of the coolest things about the definition of where does our solar system end is some of you may have noticed that for year after year after year, we kept getting a new press release of Voyager 1 or 2 has finally exited the solar system. And then we'd get another one. It has finally exited the solar system. And it was just sort of like, what the heck? How many times can you exit the solar system? And the answer was our solar system doesn't stay the same size. As our sun gets more active, it actually is able to exude a larger sphere of influence. It's able to push out further against the surrounding material in our galaxy. So our sun actually causes our solar system to have a variable size. And this is one of my favorite random tidbits of information about the edge of our solar system. So Fenric is asking, do we know if most galaxies have this large diffuse gas halo? So this kind of gas halo is due to having a superheated system. We're going to see this in active systems, and we're going to see echoes of this in systems that have recently stopped giving off recently stopped having a feeding black hole. So there are a few interesting cases of us capturing the echo, the pulse of energy that came over perhaps millennia from an actively feeding black hole and then stopped when the black hole stopped eating. This is one of those things that we don't think about a lot. In a lot of science fiction movies, you'll see someone fire a laser and this chunk of light will go moving through space. Well, you wouldn't ever actually be able to see a chunk of light going through space because it travels too fast. If it's nearby, you won't see it at least. But when we look out over the vastness of our universe and we look at things sufficiently far away, we can see the pulse of light given off by a supernova, a pulse that might be weeks in width, traveling through light years of space, illuminating gas and dust at vast distances away from us. Sometimes we just have to get far enough away to see something in perspective. And with active galaxies that do turn on and turn off over time, sometimes we get this light that is turned off in the core of the galaxy. But where it previously shined, that light is still traveling and still illuminating things as it goes. And yes, this term is indeed light echoes. So Fenric is asking, so when a nucleus is inactive, the gas and galaxy contracts back? It's not that it contracts back, it's that it stops glowing at the same temperatures. A good analogy to this is many of us have fluorescent lights somewhere in our house, and the fluorescent lights, the reason that we see them is because the gas inside the light bulb is getting excited. The electrons are bouncing back and forth between different energy levels, and when they bounce down, they give off light. Now, when you cut off the electricity going to that light, it shuts off. It's because there's nothing there to excite the electrons anymore. Now, with galaxies like this, when you no longer have the active galactic nuclei powering the X-ray, when you shut off the power, the X-ray shuts off as well because there's nothing there to excite the electrons and give off the X-rays. So I'm looking to see if there are any other questions I missed. I'm not seeing any. So please go ahead and at me with your questions. Now, today is Monday, and I don't believe we have any other streams scheduled for today, although you never know when a random rocket launch will catch our eye and we'll come here and stream it live with commentary. Tomorrow, I will be back as I am every Monday through Friday to bring you the Daily Space. This week, you're only going to see my shining face. The Daily Space is often co-hosted by Dr. Andreas Plazas, but he is currently at the World Cup. So just me this week. So I see that, no Andreas this week. He is enjoying soccer. And so he has a well-deserved vacation this week. So in addition to the Daily Space, which will run Monday through Friday at 1 p.m. Eastern, 6 p.m. London, 10 a.m. Pacific, tomorrow evening I will be hosting office hours right here, same channel, at 9 p.m. Eastern, which is 6 p.m. Pacific, 11 a.m. Wednesday if you're in Sydney, Australia. I will be answering your science questions and working on a data visualization to completely destroy, well, maybe not completely destroy, but to definitely show what happens when a hot Jupiter gets a little too hot and a little too close to its orbiting star. So I see Rocket Lab is going to try again tomorrow, so we may have another rocket launch. These are the things that we're always on the lookout for. So I see some comments about light echoes. Light echoes, I have to admit, are one of my favorite things. And I actually am the kind of human that I have my own favorite light echo. 1 second, and I'll bring it up for you. It is V838 Mon. And this particular object, I'm trying to find a time series of it. This particular object appears to be a fairly regular star that decided it was done being a regular star and was going to be an exciting star, damn it. And we're still trying to figure it out. I actually need to go back and review the literature and see how things have updated since we last observed this object. The star that makes up V838 Mon underwent a series of flare events, these extraordinarily bright flare events. Oh, my computer is trying to crash on me. These exceedingly bright flare events were captured by the Hubble Space Telescope. And when they were captured by the Hubble Space Telescope, it allowed us to map out the gas and dust around the star. So I think I've managed to pull up a view. May my computer not crash. There we go. So when it was first observed in May 2002, this was simply a brightening star. It was a kind of nova that we didn't quite have a model for. Normally we're used to outbursting stars either being a special kind of B star that is flaring for just an instant. It might be a white dwarf that's consuming material off of its neighboring star and its accretion disk goes boom. We end up with a layer of new material landing on a dense companion star. It goes boom. Most nova are related to something going boom. In this particular case, when we first looked at it, it was like, what is that? We didn't know. And as the object continued to expand, what we kept seeing was evolving structure. And what was happening here was the star in the center had at least 2 different pulsations of light in 2 different colors. And as these different colored, which means the star was a different temperature when it had each of these outbursts. So the star flared out at one temperature, flared out at another temperature. And these pulses of light created shells of light that moved outward, illuminating the material inside of each shell. And as it moved out, what we were able to see is near ground on the side and background material sequentially getting lit up. Essentially, we've been able to map out the material around this star over time as this light echo has continued to move further and further away from its host star. So this is one of my favorite light echo. No, this is my favorite light echo. There's a lot of them out there, and they're pretty darn cool, and they tell us many different kinds of things. So I'm not seeing any more questions. Well, now Azuriel asks one. Thank you, Azuriel. So that's just light that's lighting up the dust. It's just light. It's just light. It's as though the star flicked the lights on and off, and the light kept traveling away from the star. And as it did, it just illuminated dust sequentially. It's kind of awesome to think about. The best analogy I can think about is imagine having a whole bunch of people in a farmer's field that each are carrying a mammoth light, and you're hovering a drone above them. And you watch the drone footage as they move out in an expanding sphere and map out where the streams, the trails, the corn, the soybeans, all the things in the farmer's field are in a growing sphere of light. So Zuriel is asking, why does the star look brightest towards the very end of the time lapse? Less dust. So if you think about it, actually less dust is a bad answer. I think it's actually a longer exposure, because if you look, all of the stars appear much brighter. Sorry, I lied with my initial answer. It required looking longer. So here, when the star is small, when the sphere of light is smaller around the star, you have a set number of photons that thus have a large number of photons per square meter because it's a small volume. Now, as that sphere grows, the number of photons per square meter on the surface of the sphere gets fewer and fewer and fewer. And as the number of photons per square meter gets smaller, you have to take a longer exposure with your telescope. And that longer exposure causes all of these stars to get overexposed. So this is just a side effect of having to take longer telescope exposures. So I'm trying to find some good stars to use as comparison. Because the field of view on these images is also changing as we go. So I believe you have this star, this star, this star. So this little pattern right here, this triangle on the September 2nd, matches this triangle right here. So we're dealing at a different scale size, and we're dealing at a different exposure length. I hope that answered your question. And if that's it for today, I'm going to thank you one more time for coming. Please help spread the word. We do this every day, same time, same place, Monday through Friday. So please tune in tomorrow at 1 p.m. Eastern, 6 p.m. London. That's 10 a.m. Pacific. And it's bedtime if you're in the Southeast Pacific. And I will be here to put science in your brains. The Daily Space is produced by the Astronomical Society of the Pacific. We are a 501c3 nonprofit, and this is a multi-institutional collaboration. Here at CosmoQuest, you'll see myself, you'll see Dr. Andreas Plazas, you'll see Dr. Matt Richardson, who gives us an Astro 101 course every Wednesday and Friday directly following the Daily Space. We have Annie Wilson coming to us from Youngstown State University, who is showing you how she does the kinds of animation she does for planetarium shows. You never know what you'll see. You just know it's going to maybe make you a little bit smarter. So give us that follow, and get that notification about when we're going live, and we will science you. Thank you again, and wherever you are in the world, have a wonderful morning, evening, afternoon, and remember to go outside and look up. Bye-bye.